Okay, now we're recording. We're finally going to talk about computing eigenvalues and eigenvectors um, using the simplest approach possible, which is referred to as the power method, and certain variations of it. Okay. Um, Now, one thing that we saw before was if we're able to get an eigenvalue and eigenvector of any means, by any means, then we can reduce the size of a problem through deflation. So basically, getting that known eigenvalue and eigenvector out of a picture so that we can focus on a smaller matrix to find the rest. Um, so we're going to first look at the problem of computing just one eigenvector, and once we have that, we can easily get the corresponding eigenvalue. So the two together um, are abbreviated as an eigenpair because we could never have enough eigenwords, apparently. Also for convenience, even though a lot of what I'll talk about in the upcoming classes can be used for real or complex matrices, to simplify matters, we're just going to assume from this point on that A is real, but it certainly could have complex eigenvalues. Okay, so for our first approach to computing an eigenpair, we're going to make this assumption, about the eigenvalues. So lambda 1 is customarily used to refer to the largest eigenvalue in absolute value, and then lambda 2, lambda 3, and so on. But we're also, notice here we have a strictly greater than between lambda 1, lambda 2, and greater than or equal to for all others. So we assume that there's some separation in magnitude between the largest eigenvalue and the second largest. Um, we're also going to assume by the way, this assumption is going to be essential. This next assumption, not so much. We'll assume that A is diagonalizable, so we have n linearly independent eigenvectors. This is really only needed to more easily explain why the power method works when it does work. So we'll have eigenvalues lambda I, corresponding eigenvectors xi. Now, the idea is we choose some initial vector, x naught. The only requirement is that it has to be non-zero. And then we will multiply that by a to get x1, multiply by a to get x2, and so on. Now, I realize there's an unfortunate choice of notation here. So x with a subscript refers to eigenvectors. X with a superscript refers to iterates that will hopefully converge to an eigenvector. So keep the notation in mind here. So each new iterate is obtained just by multiplying a previous iterate by a. So then x sup k would be equal to a to the k times sup x naught. All right. Now here's where the non-essential assumption of a being diagonalizable comes into play. That because it's diagonalizable and eigenvectors are linearly independent, that means you can express any vector in terms of those eigenvectors. So our initial guess, x sup 0, is some linear combination of the eigenvectors. So with this representation of x sup 0 in hand, we can get a similar representation of each of our iterates. So here's what happens. So I'm going to, we'll see what happens to xk as k goes to infinity. So x sup k is a to the k times our initial vector. And here I've replaced x sup 0 with its expansion in terms of the eigenvectors. And then each term in that expansion will get multiplied by a to the k. But then each of these x's, x sub I, is an eigenvector of a. So multiplying by a to the k is the same as scaling by lambda I to the k. So then what I'm going to do is I'm going to factor out a lambda 1 to the k. So that means that in every term except the first, I'm going to have to divide by lambda 1 to the k. And we know that lambda 1 is non-zero because it's strictly largest eigenvalue. So we don't have to worry about that division by 0. And I'm writing a first term in the eigenvector expansion separately. So here we have a multiple of x1, and then we have the components in the direction of all other eigenvectors over here. Right. So if we look at whatever constant is multiplying each of these x's, so x1 here and xi here, can anyone tell me what's going to happen to the coefficients of these x's as k goes to infinity? Keeping in mind that lambda 1 is the largest eigenvalue of A.
Since lambda 1 is the largest, lambda I over lambda 1 is less than 1.
Yeah.
So the lambda I over lambda 1 to the k power is going to go to 0. And
yes.
The only remaining one is the x1.
Yeah, so the components in direction of all other eigenvectors will go to 0, leaving only this term here. So this is why this repeated multiplication by A will lead to a vector that is pointing in the same direction as x1, is parallel to it. Okay. And this is because lambda 1 is strictly greater in magnitude than all of our eigenvectors. So that is the idea behind the power method. So here's the algorithm right here. We choose some unit vector as our initial guess. Then we multiply by A. Now, if the largest eigenvalue of A is larger in magnitude than 1, then multiplying by A would lead to a vector growing in magnitude. Eventually, you might risk overflow or something. So what we do during each iteration is we normalize the vector that we get, because we really only care about the direction in which it's pointing. So here this takes the magnitude out of the equation. So under the assumptions that we've made, this iteration will cause these Q's to converge to an eigenvector of A with eigenvalue lambda 1. So a surprisingly simple approach. Okay. All right. Actually, okay. I think what I can do, since I'm in this setting, like not at the board. Okay, I'm gonna unshare for a moment and then reshare that I can do so that I can do something in MATLAB and you all can see it. Okay. Okay. All right. So what I'll do here is I will make a random matrix, say of 5 by 5. Okay. All right. And I can take a look at what the actual eigenvalues of A are. All right. So here we have both real and complex eigenvalues, but the largest eigenvalue certainly is this one. It happens to be real. Okay. So I'm going to make a random non-zero vector. Okay. And then what I'll do is I'll say x is equal to A times x. And then I'll normalize it. So basically what the power method is doing. And let's see what happens to the vector as we proceed. So here after just one iteration, Okay, whoops. Okay. Okay, especially how it keeps popping us up. I'd rather not do that. Okay. And we see that the numbers are already like they're not even changing from one iteration to the next. If I show more decimal places, okay. Okay. There's still some change in the lower level decimal places, but not much. So now if I take a times x and divide it by component-wise divided by x, we see that the values are all about the same. And sure as if we look at the eigenvalues again, we see that the ratio of the entries of a times x to those of x is essentially that largest eigenvalue. So here, the power method, after not too many iterations, managed to give me a vector that is an eigenvector of a corresponding to the largest eigenvalue. Okay. All right. So questions about how the power method does its thing. Okay. All right. Now, as for how effective it is, that depends on the ratio between the largest and the second largest eigenvalue. Okay. Actually, I think I have this backwards. Okay. You have the distance between these two subspaces decreases by roughly this factor. Okay, so if a distance is being divided by this, then yes. Otherwise, I should say lambda 2 over lambda 1. So if what this means is if lambda 2 is much smaller than lambda 1, which is kind of what we saw here, like this is actually, this right here is the second largest eigenvalue, but that's still significantly smaller than the largest. If I do absolute value of all these, okay. Oh, actually, right. This is the second largest. Because of this big gap in magnitude between the largest and second largest, that's why we saw convergence was pretty quick. Whereas if these two were much closer in size, that would drastically slow down convergence. And if the top two eigenvalues had the same magnitude, we wouldn't have convergence at all. So that's why that assumption of lambda 1 being strictly greater in magnitude than lambda 2 was essential. So if they are same magnitude but not equal to each other, the power method will not converge. So like suppose they have opposite signs, or since A is real but could have complex eigenvalues, what if the largest two occur in a complex conjugate pair? So then power method would not converge in that case. So this is a good starting point, but it has significant limitations that we need to deal with. One thing I've come across when I've actually implemented the power method is what if the largest eigenvalue in magnitude happens to be negative? Then what happens is you're multiplying an approximate eigenvector by a, because so it's being multiplied by a negative constant. So yeah, that would, so the vector appears to not be converging in that case. It is always pointing in the opposite direction from an iteration before. So one thing it's important to keep that in mind, that maybe some sort of normalization occurs. One thing that would work is, like, suppose you make sure that the first component is positive. That's one way to deal with that. The vector still will converge, even if the eigenvalue is negative. And so these little implementation details that actually tend not to be mentioned in books, that come up when you try these out. Now, if you have an eigenvector, all it takes to get the eigenvalue is you can compute what's called a Rayleigh quotient. So you compute A times your eigenvector, then take the inner product with your eigenvector, and then divide by the magnitude of the eigenvector squared. If AX1 is equal to lambda1 x1, then you'd have a lambda1 here that you can factor out, and then everything that's left would cancel out, and you'd be left with lambda1. So this is a typical way when you have an approximate eigenvector to get the eigenvalue that goes with it, the Rayleigh quotient. So once you have an eigenpair, then you can carry out deflation. And as I mentioned last time, you make a Householder matrix so that when you apply to your eigenvector, you get a multiple of E1. And as we saw previously, if you compute this matrix, this is a similarity transformation, because remember, for a Householder reflection, P1 is equal to P1 transpose, which is also equal to P1 inverse. So this is a similarity transformation that preserves the eigenvalues of A, but this matrix will be block upper triangular. So you'd have a trivial 1x1 block on a diagonal, and that's lambda1. And then the other block would be this n-1 by n-1 matrix that you can work on to get the remaining eigenvalues and eigenvectors. And actually, I think I have an exploration for that. I don't think I assigned it, though. That is a way for a matrix that has real eigenvalues, at least, to use the power method to get all of them by first using the power method on the matrix itself, and then performing deflation, then working on the matrix that comes from that, finding its largest eigenvalue, and so on. Okay. Now, so although that's not really the best way to find all the eigenvalues, but we'll come to look at alternatives shortly. But first, before leaving a power method itself, we'll talk about one application of interest that actually affects pretty much everybody. If we're applying a power method to what's called a right stochastic matrix. So a right stochastic matrix is a matrix where each entry, Pij of P, is probability of a transition from state I to state J. So because the entries are all probabilities, and you have to transition from state I to some other state, state J going from 1 to n, then the sum of all the entries in each row must equal 1. Now the diagonal entry indicates the probability of staying in the same state you're in, but there has to be some transition. Now, if you have a matrix where all of the rows sum to 1, that's the same as saying P times a vector of all ones is equal to a vector of all ones. So this is equivalent to this, just written in matrix vector form. um, and a way you can see that I can make a copy of this. Or does Pij Ej is equal to Ei. All right, so E is a vector of all ones. What we have here, this is a matrix vector product, which gives me the ith component of P times E. And we're saying that's equal to the ith component of just E. So we have a relationship like this, a matrix times a vector equals the vector itself. That means that E is an eigenvector of P, and the eigenvalue is 1. So any right stochastic matrix has that property that that it has an eigenvalue of 1, and a corresponding eigenvector is the vector of all ones. Also, because all the entries of P are non-negative, this sum right here is equal to the sum of the absolute value of all the entries in each row. And remember that the infinity norm of a matrix is defined to be the maximum row sum. Well, all of the row sums are equal to 1, so the infinity norm of P is 1. Now, we can actually conclude from that not only is 1 an eigenvalue of P, but 1 is the largest eigenvalue of P. And the reason for that is if I have any induced matrix norm, or also known as a natural matrix norm, and to refresh your memory, that is, an induced matrix norm is a matrix norm that is induced by a vector norm. So if I have AX equals lambda x, and if I take the norm of both sides of this, well, for this side, I could just pull out the absolute value of lambda. Now, the norm of AX is less than or equal to the norm of A times the norm of X. Excuse me. But then, if I cancel the norm of X, that means that the eigenvalue is less than or equal to the norm. And this is true for any eigenvalue of A. So that tells me that the spectral radius of A, which is the absolute value of the largest eigenvalue of A, is less than or equal to the norm of A for any such induced norm. So what I can conclude from this is because I have this natural norm of P being equal to 1, it's not possible for P to have an eigenvalue greater than 1, because that would violate this. So 1 is in fact the largest eigenvalue. Now, if we consider the left eigenvector of P corresponding to the eigenvalue 1, which is also an eigenvector of P transpose, the interpretation of that vector is the jth entry of that eigenvector is the long-term probability of transitioning to state J. In other words, the probability of arriving at state J in any number of transitions. So the probability that you'll eventually wind up there. Shot. So this eigenvector we can compute by applying the power method to A transpose, or not P transpose. And this is relevant to what's called PageRank, an algorithm used by Google to sort search results. So when I talk about transitioning from state I to state J, in one interpretation of that is if you're looking at the whole World Wide Web, the probability of following a link from page I to page J, if you were to index all the documents on the World Wide Web. So whenever you perform a Google search, what Google is doing is applying a power method. So they have matrix vector multiplication for a very large sparse matrix optimized as much as possible. That's the operation they care about. And the when they obtain the eigenvector of p transpose corresponding to 1, that's the probability of navigating to a particular web page in any number of links. So this way they can sort search results. One of my fellow Stanford students, back when I was there, he had asked me about the power method, and so I helped him with that. And then he ended up starting a company that made use of Google search results. And then he ended up having his company bought by Google, and he made like hundreds of millions of dollars. And like, dang, I should have gotten more involved in whatever he was doing. My advisor, Gene Golub, he was more involved, and he got some Google shares. So he made a lot of money off of Google. So sorry, I missed that boat. Oh, dang it. So even though this is the most primitive method for computing eigenvalues and eigenvectors, when you only want a particular one corresponding to the largest eigenvalue, then and if you have using a computer architecture that's optimized for matrix vector multiplication, then it's really the best way to go for in that particular instance. Actually, just for fun here, I'm going to go to MATLAB and create a right stochastic matrix. All right, so here we have a random matrix. All the entries are non-negative, but I need to scale it so that all the rows sum to 1. Now, I have to refresh my memory. I believe if I do sum of p, I think it'll sum the columns. Yeah, these are all of the column sums. But if I do sum p comma 2, that will sum the rows. So I want these row sums to be equal to 1. So here's what I can do is I can I need to divide each one of these rows of p by its row sum. So I'll get that row sum, and then I will make a diagonal matrix from those row sums. So these sums will sit on a diagonal, but then I want to multiply the inverse of this diagonal matrix by p. So whenever you're using backslash, what's on the left side of a backslash will be inverted, and that inverse will multiply what's on the right side of a backslash. So it's this inverse times p. So I'll go ahead and do that. Okay, so now if I sum the rows of this matrix, I get all ones. So now this is a valid right stochastic matrix. And if I look at the eigenvalues of p, okay, we have complex eigenvalues here, but sure enough, the largest eigenvalue is 1. And actually, if I do any matrix is similar to its transpose. So P and P transpose have the same eigenvalues. Okay, so but it's a transpose that I'm interested in. So I'm going to make a random vector again. Okay, and let's see. Actually, I'm not going to do that. I can do something a little different. So, okay. So we bring back a matrix P. Now, each entry here is a probability of going from state I to state J, or if you're thinking of in terms of World Wide Web, from page I to page J in just one link. So then if I do P squared, then that's the probability of going from state I to state J within two links. So and if I keep going, 3 links and so forth. But watch what happens if I do but keep multiplying by P. Notice that within each column, the numbers are becoming the same. Okay. So, and what we have here, if I look at, okay, I'm going to take the top row of this matrix, but I'm going to transpose it to make it a column vector. Okay. So then, if I look at P transpose times X divided by X component-wise, it's all 1. In other words, these entries that we get from any row, because all rows are the same, that's the eigenvector corresponding to P transpose corresponding to the eigenvalue 1. So you could think of it as if I was using a power method applied to 5 different vectors simultaneously, each one of them being a column of identity. Doesn't matter which initial guess I use. We're going to converge to the correct eigenvector. So, and as I mentioned before, this eigenvector indicates a probability of winding up in at a given page in any number of links, like the probability of navigating there ever. Alrighty. So questions about power method, stochastic matrices, that sort of thing.
I have a question that is not related to the stochastic matrices.
Okay.
And it's probably one that I should just know the answer to, but if we have the largest eigenvalue with algebraic multiplicity 2, it probably has geometric multiplicity 2 as well, right?
Not necessarily, because it could be associated with a 2x2 Jordan block.
Okay. So if we have an eigenvalue that the largest eigenvalue has algebraic multiplicity 2, then the power method, if the power method will still converge for the eigenvalue, and if the geometric multiplicity is 1, will it still convert? It'll still converge for the eigenvector. But if the geometric multiplicity were 2, would we just get some random vector within the span?
Okay. Right. So then what would happen in that case? Yeah, if a geometric multiplicity is greater than 1, right. So then if your initial guess, okay. Well, okay. If we go back,
It may be that this is moot because of one of our assumptions.
Yeah, but still, it's worth looking into as to what happens when that one key assumption, which is not really a realistic assumption, is not satisfied. So what would happen is I'd have, like, if I have two terms like this, like for x1 and x2, where they're both eigenvectors corresponding to the same eigenvalue lambda1, then the coefficients, like if these are the initial coefficients from initial guess, then what we're factoring out here would be the same for both terms. So based on that, you'd still have C1x1 plus C2x2, with all other terms going away. So actually, if a geometric multiplicity is greater than 1, I think it actually would converge. If the yeah, it should converge in that case. And what it converges to depends on the components in your initial vector in the direction of the multiple eigenvectors that you can have. So is whatever contribution it has in that multi-dimensional invariant subspace, that contribution will stay the same. Okay, but when if that largest eigenvalue is defective, I think I can look into this with a admittedly trivial example, but okay, so I'm going to make a the Jordan matrix. All right, but then what I'll do is I'm going to set. All right, so now we have a double eigenvalue. So this is the case where they have so the eigenvalue 2 has geometric multiplicity equal to 2, as well as algebraic multiplicity, because we have two 1-by-1 Jordan blocks for it. So what would happen is if I make my initial guess and then apply power method. Okay. So what would happen is the other entries of x should go to 0. Okay. Yeah, they are going to 0. And notice the top two entries are staying the same. Okay. And you know what I should have done earlier? Okay, actually, I'm going to go back and get the original vector. Okay, here's the original vector. And a normal. Oh, whoops. Okay, that's the initial vector. But I'm going to normalize it. Okay. Oh, okay. Yeah, these numbers are not going to be the same. Okay, because these entries are still here. Well, what happens is each time through, I multiply by j, and then I normalize the vector. But as we can see from these iterations, the power method applied to such a vector does converge. Okay. And it converges to some vector in that invariant subspace. But now, if I go back to j, and I'm going to set j row 1, column 2 equal to 1, now we have a 2-by-2 Jordan block. The eigenvalue 2 is now defective, and there's only one eigenvector going with it. So now do the same thing, like a random initial guess, and apply the power method to it, and see what happens. So the other components, 3 through 5, they still go away. Okay, and let's watch these top two components. They're not changing a whole lot, but it kind of, let's see. Actually, it looks like that second component is slowly getting smaller and smaller, very slowly. Because the eigenvector corresponding to 2 is just E1, vector of ones and all zeros. And looks like it will eventually converge to it. Whoops. Oh, I goofed. I used the wrong command. But so that's interesting. That that it's still converging, but just incredibly slow. Okay. Any questions about what happened in these examples? Oh, okay. Now, so as I mentioned, what you could do, if you use a power method to get an eigenpair, then you can use deflation, then work at a smaller matrix, get to the next eigenvalue, and so forth. But that's not really a great idea, even if the eigenvalues are known to be distinct, in which case the method would work. Well, certainly if it has real eigenvalues, but every time you deflate, that's round-off error that's accumulating. So you're losing accuracy with each eigenvalue. So there's a better way to go about it, and it's going to take some time for us to get there. But as a starting point, we use a block version of a power method that's called orthogonal iteration. So instead of multiplying A by just a vector, you're multiplying by a matrix that has R columns. And whereas before, after multiplying a vector by A, you normalize the vector. Instead, we're going to orthogonalize the block you're applying it to by computing the thin QR factorization. So not only are you normalizing each column of a block, but you're making them orthogonal to each other. So this is the algorithm for orthogonal iteration. So you start with some matrix as initial guess that has orthonormal columns. So that's what this condition means. So you multiply your U matrix by A, and then that matrix that comes out of it, you perform the thin or economy size QR factorization. So that means that UK is the same size as ZK, and then RK is a square matrix with R rows and columns. And we don't really care about RK in this case. We just want this orthogonalized version of ZK to set up the next iteration. All right, so this is the straightforward generalization of a power method to applying to a R column block. So how does it behave? As long as you have, well, there's a couple assumptions here, but this is the main one, that there's some separation between the largest R eigenvalues and all the rest of them. So this needs to be a strictly greater than. Okay. Now, so what we have here, this is the QR factorization of ZK, but rewritten so as to isolate RK, our upper triangular matrix, from QR. But ZK was defined in the algorithm to be AUK minus 1. So now we have this relationship. But now suppose that the U's are converging. So in limit, this matrix is equal to this one. So we end up with a relationship like this. U transpose AU is equal to R, which is, and R is upper triangular. So, okay. But then we end up with this relationship, AU is equal to UR, and that means that, so in the limit, as k goes to infinity, the columns of our orthogonal matrix converge to form an invariant subspace. So then we can take an invariant subspace and obtain eigenvectors from it. Now, another way to look at it is if we take the columns of U, because U is a matrix of n rows and r columns, little r. If we extend that to an orthonormal basis, then that would proceed by adding by making this matrix U perp, and I think I should have made clear that the columns of U perp are also orthonormal. All right, so because every column of this matrix is orthogonal to every column of U, the columns of this matrix span the orthogonal complement of a range of U. So now if I look at this matrix, which is square, and work out what it is, well, U transpose AU is equal to R, but AU is equal to UR. And because the columns of U perp are orthogonal to the columns of U, this 2-1 block here is 0. So in other words, we have a way to reduce A to block upper triangular form. And that means that the eigenvalues of A come from the eigenvalues of R and the eigenvalues of whatever this matrix is. All right. And R is upper triangular. So we can say that the largest R eigenvalues of A come from the diagonal of this matrix. Okay. So suppose you had a situation of A being a real matrix, and maybe its largest eigenvalues occur in a complex conjugate pair. So a power method would fail in that case. What you could do is try orthogonal iteration with little r equal to 2, and you can snap up both eigenvalues. But what's of more interest is the extreme case. We let little r equal to n. What we end up getting in that case is we still have this kind of relationship, but now all of these matrices are going to be n by n. So if the eigenvalues of A are all separated in magnitude, then what orthogonal iteration would give us is the Shor decomposition of A. Because this matrix would be upper triangular, this matrix would be orthogonal, so then the diagonal of T would give us all the eigenvalues. Now, if they are separated in magnitude, if you have any instance of, for instance, eigenvalues occurring in complex conjugate pairs or repeated eigenvalues, then this is not necessarily going to work. And even if it does work, the convergence is slow. So again, this is progress. We now have a way, under the right circumstances, of getting all the eigenvalues of A. So we're getting there, but there's still a lot of work to do. More what I can talk about in today's class. All right, but as far as making this process more efficient, we're going to deal with that later. Like on Thursday, we can make some progress addressing that. But for now, we're going to take a closer look at what's happening when we use orthogonal iteration in the case of R equal to n. So when I'm carrying out the orthogonal iteration algorithm, so this algorithm, but with R equal to n. So our initial matrix is an n by n matrix. For instance, we could just choose identity. All right. So carrying out this process, if I define TK to be UK transpose AUK. Then, based on this definition, I have TK minus 1 equal to this. But from the algorithm, AUK minus 1 is the same as ZK. That's how ZK was defined. But ZK is then QR factorized to give us UK RK. So then I take these matrices that have orthonormal columns and I multiply them together, and then I get this matrix that I'll call QK that also has orthonormal columns. In fact, this is a n by n orthogonal matrix, because the product of any two orthogonal matrices is also an orthogonal matrix. So what that means is I have a QR factorization of TK minus 1. And RK is the R from that QR factorization. Okay. Now, let's look at the next matrix, TK. Here's how it's defined from up here. And then what I do is I'm going to insert in the middle of this a UK minus 1, UK minus 1 transpose, because UK minus 1 is an orthogonal matrix, so this whole thing is identity. But then AUK minus 1, that's how ZK is defined, so I'll go ahead and put that in there. But ZK is QR factorized to give me UK RK. This is identity, because UK is an orthogonal matrix. And this right here is how QK was defined. So now I have this. So if I have TK minus 1, I QR factorize it, I can get the next TK by multiplying those QR factors in reverse order. Oh. I mean, I can continue this process. I can then take TK, QR factorize it to get like QK plus 1, RK plus 1, multiply those in reverse order. That would give me TK plus 1 and so on. So I can just keep doing that. Also, if I keep in mind how I got TK, so it's RK QK, but RK came from QR factorization of TK minus 1. So in effect, what I'm doing is I get TK from TK minus 1 by performing an orthogonal similarity transformation, multiplying by QK transpose on the left, QK on the right. So the eigenvalues of these T's are all preserved. And in the end, you keep in mind how the T's are defined. TK was defined this way. So if T converges, then I have this. T is equal to U transpose AU. And T is upper triangular. So that's a Schur decomposition. So now I have a rewriting of orthogonal iteration in this R equals N case into what's called QR iteration. So I choose an initial orthogonal matrix. I could just choose identity, for instance. And then I compute this to give me T0. T0 will have the same eigenvalues as A because this is their similarity transformation. And now I just keep working on these T's. QR factorize, multiply factors in reverse order. Then QR factorize that and multiply in reverse order. Just keep going. So this is the simplest form of what will eventually become the QR algorithm, the standard approach to computing all the eigenvalues of a matrix. Now, this is a very simple form of it, but it's the foundation. Let's try this out. Whoops. Okay. All right. Here's my matrix A. So then I'll do A equals QR equals QR of A equals R times Q. All right. Let's see what happens. Notice we're starting to get some small entries below the diagonal. I notice we have this rest of this column is all 0. Having a hard time getting any other triangularity, but if we look at the eigenvalues of A, they're nearly all complex. So, oh wait, oh okay, we have 3 real eigenvalues and 2 that are complex. Okay. So one of those, I look at the eigenvalues again. The smallest one we can see down here. The largest one we can see up here. This 3x3 matrix in the middle would account for the 2 complex eigenvalues and a remaining real eigenvalue. But all three, whoa. Not sure what happened there. Okay. All 3 of those eigenvalues are close in magnitude, which is why we're not getting much convergence. And I would hope that eventually, if slowly, the remaining real eigenvalue would be teased out of all this. And I think it's slowly but surely happening. Like this entry right here is getting smaller and smaller. So is this one. And I think if I kept at this long enough, it would eventually go away. But that's what happens if the eigenvalues are clustered closely. Just as with the power method, convergence is quite slow, and something has to be done about that. And that's something that will be addressed in upcoming classes. Wow, what a pain this is. Okay, whereas if the eigenvalues had been more separated, I could have stopped this a long time ago. But see, we are getting smaller, and if I look at the eigenvalues, we have 0.5684. Here we're up to 0.5681, so it's getting there. Whereas these 4 entries, this will become a 2x2 block along a diagonal, and everything I'm doing here, QR factorizing, multiplying the factors in reverse order on a real matrix would still give you a real matrix. So there's no way using these operations I could ever get an upper triangular matrix of complex eigenvalues along a diagonal. But that's okay. I mean, if you have something that's block upper triangular with 1x1 or 2x2 blocks on the diagonal, we can certainly work with that. So sure enough, we can see all 3 real eigenvalues on a diagonal. This 2x2 block accounts for the complex conjugate pair. All right. So demonstration that QR iteration can work. But computing a QR factorization of a general matrix takes order n cubed operations, and that's every iteration. And as you can see, especially if you have closely clustered eigenvalues, you might be performing a lot of iterations. So this process is still way too computationally expensive, but that's something we'll work on. So we could start out by reducing A up front to a form that for which QR can be carried out more efficiently. Okay, and this is what I showed you in MATLAB. A is real matrix with complex eigenvalues. Yes, it doesn't converge, but we do get this quasi triangular form if he's 1 by 1 or 2 by 2 blocks. So that'll be enough for our purposes. So for real matrices in the Alpha case where you can have complex eigenvalues, that's all we're after. We're not going to try to reduce to upper triangular form, but block upper triangular with 1 by 1 or 2 by 2 blocks. I mentioned earlier it's called the real Schur form. Okay. That's the end of the notes. Okay, so significant strides were made today towards an algorithm that can compute all the eigenvalues. So at least we have an algorithm that can do that. It just needs some work to make it a whole lot more efficient than it is now. Okay. Are there questions?
No,
Oh.
sir.
Okay, I see Nemo left. Alrighty. Well, we'll keep us going on Thursday then. Okay.